Okay, good afternoon, class. So at this point we have completed exercise 1 and we've dealt with the proportionality theorem. Not so? Then we went, if you go on and you see the theorem 1 converse, which is the converse of the proportionality theorem. That is not examinable. We can spend 2 lessons on it, but it's not going to help us much. Okay? So we're not going to do the converse theorem. Okay? So coming from the midpoint theorem, the midpoint theorem was done in grade 10. Not so? Okay? Now in the midpoint theorem, get somewhere to write. It's a very important theorem to understand and its application. Okay? So the midpoint theorem. In the midpoint theorem, this theorem is a special case of theorem 1. Okay? The proof of this theorem is not required for examination purposes. I know in grade 10 we gave you the theorem and we asked you to prove it, but it's not for the grade 12 syllabus. Okay? It says that the line segment joining the midpoints of the 2 sides is parallel to the third side and equal to half the third side. We are told if AD is equal to BD and AE is equal to AC. Or if you look at it this way, if you had taken, that is ABC, and you took the midpoint of AB and the midpoint of BC, make that E, and you connect that. That's basically what they're telling us. If that is the case, then we can conclude that DE is parallel to BC, as well as BC would be equal to double DE. Do you see that, people? So if you read here, they say if AD is equal to BD and AE is equal to EC, then DE is parallel to BC and BC is going to be double DE, or DE of course is going to be the half of length BC. Okay, that was the midpoint theorem. Then there was a converse to this theorem, the reverse to this theorem, which states first get it. Yeah, it says not for examination purposes, but this is actually tested. It was tested in last year's exam. Okay, that is why I'm taking time now to explain this. I've done it with the last year group as well, but they were a special kind of group. You guys are more special than me, no? Guys must do well, no? Mustn't it? Embarrass me when we mark at the end of the year, no? Then everybody knows which school I'm from. So I must talk a lot, you understand? And last year I knew I hadn't to talk a lot. But this year, I'm sure we're going to shine. No? You're already closing your eyes. Oh, here. People, Theorem 2 is the converse of Theorem 1. Okay. So we are told the line passing through the midpoint of one end. The line passes through the midpoint of one side of the triangle. The midpoint is now the middle. No? Parallel to the other side. Parallel to another side. Bisects the third side third side and is equal to half the length of the side it is parallel to. So if this is the case, we have that being equal to that there, which is ABC, DE. If this was if D was the midpoint of AB, and DE was given parallel to BC, the lines were given parallel, then what can we conclude? Then AE is equal to EC. And BC is going to be double DE, or DE will be the half of BC. And if you use this, people, it is, and your diagram looks like this. Your reason here is the converse of the midpoint theorem. You see that? If you use the previous, theorem 1, your reason here is the midpoint theorem. Okay? So it's either the midpoint theorem or the converse theorem. Okay? You guys understand? Sorry? Say again? So leave it so. Okay? Was did the school send the teach team to the school today? No.
Just one also.
One girl. The one girl represented our school. Also she wanted to. Okay? 2 minutes is a long time. Okay, let me sort out the rest of it quickly. Okay. Okay, there's theorem 2. I'm just going to pause the video so now. Okay, so now we're looking at the Similarity Theorem. We're on page 259. You guys remember about when last did you have similarity? When did we do similarity? In grade 10. 10. You did similarity in grade 10. Which school were you at? Sorry? Oh, you weren't here last year, sorry. Okay, you knew. Welcome. You new to our school? Okay, then you knew. First time I see you. But welcome. I know they didn't do it in grade 10, man. That's why I'm surprised that you said grade 10. We did it in grade 9. Okay, but doing it in grade 10 is a good thing because it keeps the theorem fresh in your head. Okay. So you the most experienced in this theorem at this point. You wish? Okay. People, so let's just change the focus of this screen here quickly. Don't forget, we must change it back when we do the proof of this theorem, okay? In the last video, we didn't change it back. By mistake, okay? That wasn't on purpose. People, similarity theorems. Now, in the past, we spoke about two shapes are similar if they have the same shape but not necessarily the same size. So we say that all equilateral triangles will be similar. Why? Because why they are the same shape but not necessarily the same size. Okay? So, for example, we are told that, just take this off here. We are told that, for example, polygon EFGH. What's a polygon? It's a closed figure made up of edges. No? It's made up of any amount of sides. Okay. Polygon EFGH is the enlargement of polygon A, B, C, D. You all agree with that? Okay. By a scale factor of 2, which means to say 2,75 times 2 is 5.5. 2 times 2 is 4. 1,95 times 2 is 3, and 2 times 1 is 2. You all agree with that? Those shapes are similar. They're exactly the same shape, but they are enlarged. Not so? Right. Then we are told that two conclusions must both satisfy for two polygons to be similar. The corresponding angles must be equal, as you can see here. Angle A is equal to angle E, which is 35. Angle D is equal to angle H, which is 76. Angle B is equal to angle F, which is 155. And angle C is equal to angle G, which is 96. Okay. People, these interior angles of a four-sided figure will always add up to what? 360 degrees. Why? Because the polygon. It's because we can make two triangles out. Each triangle adds up to 180. So if you had a five-sided figure, okay, 5 sides, is what? A pentagon. Not so? 5-sided figure is a pentagon. And how many triangles can you fit in a pentagon? 3. The 3 times 180 is 540. So the interior angles of a pentagon adds up to 540. So you can take any amount of sides, put the triangles into it, and by connecting the vertices as you see I did now, and then you count the triangles, you multiply by 180. Otherwise you can say, you could have said 5 minus 2, and what's 5 minus 2? 3, and 3 times 180 is also 540. Now if it's a 10-sided figure, it's going to be 10 minus 2, which is 8. 8 times 180 is 1000 and something. Let's check what it is. Something 64. 681440. Just check if that's right. Correct? Right. So what if it was 8 sides? 8 sides, what do I do? 8 minus 2, which is 6. 6 times 180, which is 1080. Does it make sense? So whatever amount of sides there are, you minus 2 and you multiply it by 180. You all okay with that, no? Yes? Because if you got a, say, let me just show you something. Question is why are we minusing 2? Let me just show you. I think you forgot the assignment we did. We had 3 sides, that was 180. Yeah? Then we had 4 sides. Then 2 triangles can fit into it. So it's 1 triangle. Yeah? So 2 triangles, which is 360. So if we had a 5-sided figure, so we can get 3 triangles. Can you see that? We had a 6-sided figure, another what's the word for a 6-sided figure? Hexagon. So how many triangles can you fit in here? 4. 7-sided figure, 6, 7. 1, 2, 3, 4, 5, 6, 7. 7-sided figure is a heptagon. No? So these go 1. So it's 1, 2, 3, 4, 5. Can you see? So 4 times 180 is 360. No. 4 times 180? This is 5, 14, eh? 4 times 180, so it's 186, 72, 720, and 800, 900. So what do you notice here? This was 3 sides, 4, 5, 6, 7. But what do you notice in relation to how many triangles you can get out of it? 3 sides, 1 triangle. 4 sides, 2 triangles. 5 sides, 3 triangles. Can you see that? So what's the difference of this? There's a difference of 2. So in general, if it's n amount of sides, so that would simply be n minus 2 times 180. So if it's 12 sides, what do we do? So if n is 12, if it's 12 sides, it's going to be 12 minus 2 times 180, which is 1800. You understand why we minus it? Okay. Anybody else want to confuse us? No? We're taking you too far here, no? Just change the focus again here. So we're continuing reading on this page here. So you see 2 conditions must both be satisfied for the 2 polygons to be similar. The corresponding angles must be equal, and the ratio of the corresponding sides must be in the same proportion. So in other words, we spoke about A, B. If we say 4 over 2, what's 4 over 2? 2. Not so. What is 2 over 1? 2. What's 3,9 divided by 1.795? 2. 5.5 divided by that is 2. Or we could have gone the other way around. 1,95 divided by 3,7 is half. And so on and so on. You all understand? Okay? So the condition is all the angles, the corresponding angles must be the same, and the sides must be in, the corresponding sides must be in the same proportion. Okay? Now here's an example where the first condition is met. Because is the corresponding angles of A, B, C, D equal to the corresponding angles of E, F, G, H? Yes. All the angles are 90 degrees. Not so. But are the corresponding sides in proportion? No. Because here we got AB over EF, which is 2 over 2, which gives you a ratio of 1. AD over EH. AD over EH is equal to 5 over 2, which is not the same as 1. Or what they used was BC over EFG is 5 over 2, which is not 1. So in that case, the first condition is met. The corresponding angles is equal. But is the sides in proportion? No. So is shape A, B, C, D similar to E, F, G, H? No. Okay, why? Because the sides are not in proportion. Alright, you guys understand? Right. With similar triangles, only one of the two conditions needs to be true in order for the two triangles to be similar. With similar triangles, only one of the two conditions needs to be true. Or triangles. Okay, here we were busy with a four-sided figure. In a triangle, if the angles are similar, okay, if the corresponding angles are equal, then the sides has to be in proportion. That is now the condition for triangles only. This is squares or pentagons or so on, then it's not going to work. Okay, with a triangle, if the corresponding angles are equal, the sides are in proportion. If the sides are in proportion, then the angles are equal or equiangular. Okay. Now we're looking at Theorem 3. Okay, we're going to prove this theorem quickly. It will probably take us to very close to the end of the lesson. Yeah? Yes? Yes. So we're on page 260. You will definitely be tested on this in your next exam. As we gave you the other one that was tested in your cycle test, this will be tested in your control test. In your June exam, we won't tell you which one is going to be tested. Okay? So try and take note of what's happening here, so that it's easier for you to go study it when you get home. Okay? Theorem 3. So write that down. Theorem 3 on page 216. The corresponding sides of two equiangular triangles are in the same proportion, and therefore the triangles are similar. Okay? Now in the exam they won't ask you a question like this here. They would leave this part out. Okay? So let's recut this. This is as AB over DE is equal to AC over DF. They would ask you to, they tell you, given that angle A is equal to angle D, then angle B is equal to angle E, and angle C is equal to angle F. That would be given to us. The question says you're required to prove that AB over DE is equal to AC over df. That's what you are required to prove. So draw the triangles quickly. Alright, so here we go. So we are given that angle A is equal to angle D, angle B is equal to angle E, and angle C is equal to angle E. The question says you are required to prove that AB over DE, you prove that AD over DE is equal to AC over DF. That's what we are required. Okay. So as we did before, all our theorems always starts out with a what? Construction. So this one's going to be no different. Okay? Just put this at the bottom. So all of these are going to start off with a construction as we normally do. Okay? So we start off with construction. Okay. So we're going to mark G on AB such that, so we'll mark G on AB such that AG is equal to D. What does that mean? That means to say the length of AG is equal to the length of D. You guys got it? That's number one. Yes? From the 8. You want to put the M instead of a G. You can put the M. Yes? Oh, if you want to put the O, no problem. But could you have put an E there? Because that is an E already. You understand? You can use any letter you want to use. Alright? Then we're going to mark. Where do you think is going to go here? H, yes. Mark H on AC such that AH is equal to DF. Okay? Then we're going to join GH. Okay. Make this realistic. Oh. This is about the same size, no? Alright, you all got that. That is one mark already in the exam. Out of 6. Okay? The proof. Here's the proof. You all understand that, no? Alright, proof. So what we're going to do is we're going to prove congruency in triangle GAH and EDF. We're going to prove that these two triangles are congruent. So where do we start? We say in triangle AGH and triangle DEF. What can we say so far of the two triangles? There are four cases of congruency. What are the four cases? Side, side, side? Side, angle, side? Right hand hypotenuse side? And our favorite? Angle? Angle? Side. Yes. So what can we say about this here? No, we must first prove congruency. How do you prove congruency? GA is equal to? Sorry? Listen. GA is equal to? ED. Why? Construction. We must construct that story. Not so. What else can we say? Angle A is equal to angle DY. The same. Given. What's wrong with you? One more. AH is equal to DFY construction. Another 2 marks in the back. No, not yet. Now what? You are thought you were gone out. Now what can we conclude? Therefore, triangle AGH is congruent to triangle DEF. Why? Side, angle, side. Not so? But side, angle, side. Now, you see that angle, this AGH, this angle here, is the same as which angle? DEF, angle E. How do we get that? Congruency. Well done. We have just proven congruency. So if we prove congruency, the two triangles are exactly the same size and the same shape. All the corresponding angles are equal and all the corresponding sides are equal. Okay. So we can say that AGH, therefore AGH is equal to angle E. Why? Because triangle AGH is congruent to triangle DEF. Okay, so this angle here is equal to that angle. Okay? But this angle here is also equal to which angle now? Angle B. Why? Because it's given that angle E is equal to angle B. That was given to us, not so? Yeah, was given. So, if angle AGH is equal to angle E, then AGH has to be equal to B as well. Not so? Now, if those two angles are equal, what can be now concluded about GH and BC? They're parallel. Not so? It's page 260. They are parallel. Not so? So we can say therefore GH is parallel to BC. GH is parallel to BC. On what account are they parallel? Corresponding angles are equal. Now normally when we use corresponding angles, what do we say? When we use corresponding angles, we say that you name the lines that are parallel, not so? But here we are saying they are parallel based on the fact that corresponding angles are equal. Can you see the F being formed here? For those of you who don't know what corresponding is, UF. No? Right. Is it put down there? Okay. Now how is that going to help us? How is that going to help us? Coming from the previous theorem. Okay? If that was A, G, E, C, and H, if those lines are parallel, from the previous theorem, what could you have said? From the previous theorem, what could we have said? People, you wrote on this today, come on. Oh, can't you see? AG is over GE is equal to AH over HC. Not so? So, coming from that idea, from that theorem, we can say, yeah, same story. Not so? And I'm going to use that now, okay? I'm going to say that AG over GB AG over GB is equal to AH over HC. And what's the reason there? The proportionality theorem with GH parallel to BC. Not so? So the sides, so we're using a proportionality theorem. Okay? But if you look at what was needed to be proven, it was AB over DE, which is that one on top. Not so? So that is actually the other variation. I made a mistake. We must actually go, since looking at what they want, we got AB and DC. So we got AG, AC and AH. So we go again. So it's going to be AB over AG, AB over AG, AB over AG is equal to, this thing is starting, AB over AG equals AC over AH. Let's check this thing still recording. Okay, so it's AG over AB. Now AB over AG is equal to AC over AH. Right. And what's the reason there? You see it's your proportionality theorem with GH being parallel to BC. Okay. But if you look at what we have, you see AB we have now on its place. AC we have. But AG and AH we don't, it's not on its right place. Not so. However, we know that AG, what is AG equal to? AG is equal to DE. How do you know that? Construction. And AH is equal to DF. Can you see that? Also construction. So we say, since AG is equal to DE and AH is equal to DF. So in other words, we can of course replace this and that now, not so. Therefore AB over DE has to be equal to AC over DE. And there we have proven that theorem for 6 marks. Okay. Any questions? Yes? Any questions? Sorry?
Isn't it over DF?
DF. So it's AB over DE and AC. So it's going to be AH and DF. AH and DF. So it's AH and DF. Yes, you're right. Absolutely. I wrote DE twice, sorry. Right. Now in that video that I made with regards to all the theorems, this is the last theorem in that video. Okay? So if you want to watch the theorem again and again, the other video has this theorem as the last theorem in that video. Right? You know what video I'm talking about? You're shaking your head. The other day I gave you the video and I sent it to your phone. I showed you where it is on the that video. The previous theorem is at 41 minutes. No? This one is after that theorem. Okay? So I've done it again. So you can either watch it from here or from that point. Okay? So let's look at the example. Hey. So we're looking at example 8 on page 261. Example 8 on page 261. Yes? I thought you were going to ask a maths question. All right. Example 8, page 261. Right, throw it quickly. We wait for her to get back. I'll give it 2 minutes. Come, people. You finished drawing? Come, listen, in this class we don't have much time. I know in your other class you can take things easy. Am I right? Huh? Yeah, the people here just want to do maths. The people is, not them. Because when I get home, I can't do maths. What's his scale? The wife, she don't want me to do maths at home. So I must get, she tell me I must get enough maths at school. Do enough maths, yeah? So I can feel fulfilled when I get home, you understand? Right, here we go. We can't wait for Ashley any longer. So we are told that in triangle PST, which is a big triangle there, TS is perpendicular to PS. So TS is perpendicular to PS. Okay? Which means to say this is 90. Then we are told that RQ is perpendicular to TP. Okay. The question says prove that triangle PRQ, so PRQ is similar to triangle PST. PST, the big triangle. Okay? So as we did before in concurrency, we start similarity of the same. How do we start off with it? We say in triangle PRQ and triangle PST. So what can we say about those two triangles? Remember, it's triangle PRQ and PST. What can we say about those two triangles? Remember, when we prove similarity, what do we prove? One of two things in a triangle. We either prove that all the angles are equal, or we prove that the sides are in proportion. One of the two. Okay? Then we don't have lengths of sides here. So we're going to talk about the angles that are equal. So what can we say about those two triangles I've highlighted earlier? Angle P is in both triangles, not so. So angle P is a common angle. Angle P is in both triangles. What else can we say? What else can we say? What else can we say, people? Okay, we'll start again here tomorrow. Okay, now homework today.
My apologies for the late start. It is registered now. My apologies for the late start. Would you like to register, please?
But I feel bad now not giving you homework. Huh? Alright, listen for homework. You must go learn the proof of this theorem. Okay. Write it over twice or thrice. You should get it right. Okay. People, enjoy the rest of your day. Good afternoon, class.